High above our heads, invisible rivers of air circle the planet at speeds that would tear the roof off a house. And almost no one down here ever gives them a second thought. They have no color, no sound, no shadow. They cannot be photographed from the ground, cannot be felt on skin, cannot be seen in any sunset. And yet, these hidden currents decide, more than almost anything else on Earth, whether next week brings sunshine or a blizzard, a heat wave or a flood, calm skies or the kind of storm that makes the evening news. For most of human history, we lived beneath them without knowing they existed. Now, in laboratories and satellite control rooms scattered across the globe, scientists are watching them more closely than ever before, because something about their behavior appears to be shifting, and nobody is entirely sure yet what that shift will mean. This is the story of the jet stream.
Not a myth, not a prediction of doom, but a real physical feature of our atmosphere, discovered almost by accident, misunderstood for decades, and only now, with the help of satellites, supercomputers, and 70 years of accumulated data, beginning to reveal its secrets. It is also the story of a scientific mystery still being solved in real time, one where researchers openly disagree, where models produce conflicting answers, and where the phrase, "we don't know yet," is used honestly rather than as a dodge. If you have ever wondered why a heat wave can sit over one region for weeks while a neighboring country floods, or why winters occasionally deliver a polar blast to places that rarely see snow, the answer very often begins several miles above the clouds, in a ribbon of wind that never stops moving. To understand why researchers are paying such close attention right now, it helps to start with a simple, almost embarrassing question. What exactly is the jet stream? And why does something so powerful remain so unfamiliar to most people who live directly beneath it? Picture the atmosphere not as an empty space, but as an ocean of air, layered by temperature and pressure, restless and constantly rearranging itself. Somewhere between 9 and 16 kilometers above the surface, near the boundary where the troposphere gives way to the stratosphere, air masses of very different temperatures brush against one another. Warm, moist air drifts up from the tropics. Cold, dense air spills down from the poles. Where these two very different bodies of air meet, the temperature contrast becomes extreme over a short distance, and that contrast is the engine that drives the jet stream into existence. Physics offers a fairly elegant explanation for what happens next. A sharp temperature gradient creates a similarly sharp pressure gradient, and air always tries to flow from high pressure to low pressure. Left alone on a stationary planet, that flow would simply move directly from the cold side toward the warm side. But Earth is not stationary. It spins, and that spin bends the moving air sideways through what is known as the Coriolis effect. The result is not a straight river of wind, but a fast-moving current that wraps around the entire planet, generally flowing from west to east, threading a wavy path between the pole and the equator. This is the jet stream, a high-altitude corridor of wind, often only a few hundred kilometers wide, but thousands of kilometers long, where speeds can reach 200, 300, even in extreme cases, well over 400 kilometers per hour. There is more than one of these currents circling the Earth. Meteorologists generally distinguish between the polar jet streams, which sit at the boundary between cold polar air and milder mid-latitude air, and the subtropical jet streams, which form farther toward the equator, where tropical heat meets the temperate zone. Each hemisphere has its own version of both. The polar jet, the one most relevant to weather across North America, Europe,
and northern Asia, is the one this film will follow most closely, because it is the one whose behavior has captured the attention of atmospheric scientists in recent years. What makes the jet stream so consequential is not simply its speed, but the role it plays as a steering mechanism. Large-scale weather systems, the sprawling zones of low and high pressure that bring rain or clear skies, do not simply drift wherever they please. To a remarkable degree, they are carried along by the jet stream, the way leaves are carried by a river current. When the jet stream runs in a relatively straight, fast line, weather systems tend to move through quickly, and conditions change from day to day in a familiar rhythm. When the jet stream instead develops large, slow-moving loops, sometimes called Rossby waves after the meteorologist who first described them mathematically, weather patterns can become locked in place. A ridge of high pressure trapped under one of these loops might deliver weeks of unbroken heat and drought. A trough on the other side of the same wave might funnel cold air unusually far south, or hold a storm system over one location until rainfall totals climb into record territory. None of this was understood, or even suspected, until well into the 20th century. And the way it was discovered says something important about how difficult the jet stream is to observe directly. The first hints came not from weather scientists, but from pilots. During the Second World War, American bomber crews flying at high altitude over Japan reported something bewildering. Their aircraft, pointed due east, were being pushed backward, sometimes losing more than 100 kilometers per hour of ground speed, as if flying into an invisible wall of wind. Bombing runs that should have taken a predictable amount of time were thrown wildly off course. Fuel calculations failed. At first, some crews suspected instrument error. It took repeated encounters and careful comparison of flight logs for meteorologists to conclude that something real and enormous was happening at altitude. A river of wind moving far faster than anything documented at ground level. Independently, a Japanese meteorologist named Wasaburo Oishi had already been tracking something similar in the 1920s, using weather balloons launched from a station near Mount Fuji to trace unusually fast upper-level winds. His findings, published in Esperanto in an effort to reach an international audience, were largely overlooked outside Japan at the time, a footnote in the history of a discovery that would later be treated as an American wartime revelation. It is one of those quiet ironies of science. The phenomenon had already been measured and described years earlier, but the infrastructure to notice, translate, and act on that work simply was not there yet. After the war, as weather balloon networks expanded and aircraft-based observation became more systematic, meteorologists began mapping the jet stream in earnest. They found that it was not a fixed structure at a fixed latitude, but a restless one, migrating north and south with the seasons, splitting into multiple branches, sometimes weakening to a broad, diffuse flow, sometimes intensifying into a narrow, howling corridor of wind. Commercial aviation quickly learned to exploit it. Eastbound flights across the Atlantic and Pacific began deliberately routing through the jet stream to shave hours off travel time, while westbound flights routed around it to avoid the headwind penalty. To this day, the jet stream is one of the most consequential and most invisible forces shaping modern air travel, quietly altering flight times by half an hour or more, depending on which side of the current a plane happens to catch. But it was in the field of long-range weather forecasting that the jet stream's true significance became clear. Meteorologists studying decades of upper atmosphere data began to notice a consistent pattern. The The position and shape of the jet stream on any given day corresponded closely with the weather unfolding beneath it. A jet stream diving unusually far south brought cold outbreaks with it. A jet stream retreating far to the north left the door open for warm, stagnant air to build. As computer models improved through the second half of the 20th century, tracking and predicting the jet stream's movements became one of the central tasks of operational forecasting. The hidden skeleton beneath every 5-day and 10-day forecast broadcast on television or displayed on a phone screen. By the final decades of the 20th century, the jet stream had gone from a wartime mystery to one of the most thoroughly documented features of Earth's atmosphere, tracked continuously by weather balloons launched twice daily from hundreds of stations worldwide, by commercial and research aircraft, and increasingly by satellites capable of estimating wind speed and direction from space. This decades-long record is precisely what allows scientists today to ask a question that would have been impossible to answer with any confidence even 30 years ago. Is the jet stream changing? And if so, why? Today, tracking the jet stream is no longer a matter of chasing anecdotal reports from startled pilots. It is an enormous, continuous, multi-layered observation system, one of the most extensive monitoring efforts ever built for any single feature of the natural world. And it is this system that gives modern researchers the confidence to say something is happening at all. The most basic layer of that system has barely changed in principle since the 1940s, even as the technology behind it has been transformed. Weather balloons, known formerly as radiosondes, are still launched twice a day from roughly 900 stations scattered across the globe, carrying small instrument packages that measure temperature, humidity, pressure, and wind as they rise through the atmosphere. Each balloon transmits its readings back to the ground before it bursts high in the stratosphere, and each flight adds one more data point to a record that now stretches back more than 70 years in the most consistent locations. It is a strangely old-fashioned method, sitting at the foundation of an extremely modern science. A rubber balloon and a small radio transmitter, repeated hundreds of thousands of times, forming the backbone against which every satellite and every computer model is checked and calibrated. Above the balloons, a fleet of satellites operated by agencies including NASA, NOAA, the European Space Agency, and EU EETSAT continuously observes the atmosphere from orbit. Some of these satellites measure temperature at different altitudes using infrared sensors, effectively mapping the same temperature contrasts that give rise to the jet stream in the first place. Others track the movement of clouds and water vapor across successive images, allowing scientists to estimate wind speed and direction indirectly, a technique that has become increasingly precise as image resolution and processing speed have improved. Still others use GPS radio occultation, a method that measures how satellite signals bend as they pass through the atmosphere, providing extremely accurate vertical profiles of temperature and density with global coverage that no balloon network could ever achieve on its own. Commercial aviation adds another enormous stream of data, almost without anyone noticing. Thousands of commercial aircraft are equipped with sensors that automatically report temperature, wind speed, and turbulence at cruising altitude, feeding that information directly into weather agencies in near real time. Every transatlantic flight, in a sense, becomes a temporary research instrument, contributing measurements exactly at the altitudes where the jet stream operates. Programs coordinated through the World Meteorological Organization
now assemble millions of these aircraft-based observations each year, a volume of data that would have been unthinkable to the balloon and clipboard meteorologists of the 1950s. All of this observational data feeds into a further layer: reanalysis data sets, enormous computational products that combine decades of historical observations with modern weather models to produce a consistent, gridded record of the atmosphere stretching back many decades. One of the most widely used of these, known as ERA5, and maintained by the Copernicus Climate Change Service on behalf of the European Center for Medium-Range Weather Forecasts, blends millions of individual observations with sophisticated physical models to estimate what the atmosphere was doing at every point on the globe, several times a day, going back to the middle of the 20th century. It is through data sets like this one that scientists are able to calculate long-term trends in jet stream position, speed, and shape, with a level of statistical confidence that would have been impossible using raw station data alone. It is worth pausing here to appreciate just how much has to happen for a single sentence like, "The jet stream is changing," to be scientifically defensible. Researchers cannot simply glance at a windy week and declare a trend. They must first establish what the jet stream's behavior looked like reliably across many decades, filter out natural year-to-year variability driven by phenomena like El Niño and La Niña, account for known cycles like the North Atlantic Oscillation, and only then look for a signal that persists after all of that noise has been accounted for. This is painstaking, often unglamorous work, involving statistical techniques with names like wavelet analysis and empirical orthogonal functions, methods built specifically to separate genuine long-term shifts from the ordinary chaos of weather. And when researchers apply these methods to the accumulated decades of jet stream data, several patterns do emerge, consistently enough across multiple independent studies that they are treated as reasonably well established, even while the underlying causes and future consequences remain the subject of active investigation. One recent global review published in a leading Earth science journal in 2025 synthesized decades of research into how eddy-driven jet streams behave across different seasons and regions, concluding that both the strength and the position of these currents show measurable long-term change, though the details vary considerably from one region of the planet to another. In some areas, the changes point toward stronger, more concentrated winds. In others, the story is about shifting position rather than shifting strength. There is no single universal storyline. There are several overlapping ones, each supported by a different strand of evidence. Modern climate models add another crucial dimension to this picture, allowing researchers to run the physics of the atmosphere forward under different future scenarios and see what emerges. A study published in 2026, using an ensemble of 40 separate climate models, examined how a specific branch of the jet stream, the Eurasian subtropical westerly jet that steers weather across Central Asia, is projected to behave through the rest of this century. The researchers found that this particular current is expected to strengthen and shift southward during summer months, driven by a combination of rising greenhouse gas concentrations and declining atmospheric aerosols from cleaner air policies. Intriguingly, the study suggested this shift could actually ease drying trends across parts of Central Asia by carrying more moisture into the region. A reminder that the consequences of jet stream change are not uniformly negative or uniformly dramatic everywhere. They can be regionally specific, sometimes even counterintuitive. Elsewhere, a separate line of research led by a University of Chicago atmospheric scientist and a colleague at the National Center for Atmospheric Research examined not the average jet stream, but its most extreme winds, the fastest moving cores within the broader current. Their modeling work suggested that these peak wind speeds could accelerate by roughly 2% for every additional degree Celsius of global warming, with the very fastest winds speeding up even more sharply than the average flow. The researchers were careful to note that while record-breaking jet stream speeds have already been observed in recent decades, the statistical signal distinguishing this trend from ordinary variability is not yet strong enough to be called definitive. It is, in their own words, a signal expected to emerge more clearly over the coming decades if current emissions trends continue. In the Southern Hemisphere, a separate international research effort used a novel statistical storyline approach designed specifically to explore multiple, physically plausible futures under deep uncertainty, and concluded that roughly half of the shifts already observed in the Southern Hemisphere jet stream over recent decades can be attributed directly to human-driven warming, a striking figure that helped refine the confidence range used in subsequent climate projections. Taken together, this expanding web of satellites, balloons, aircraft sensors, reanalysis products, and supercomputer simulations gives scientists today a view of the jet stream that simply did not exist a generation ago. It is not a single dramatic photograph revealing an obvious transformation. It is closer to thousands of overlapping puzzle pieces, each one imperfect on its own, gradually assembling into a picture that most researchers agree shows real change underway, even as they continue to debate precisely how large that change is, how fast it is proceeding, and what it will mean for the billions of people living beneath these currents. If there is one word that recurs again and again in recent jet stream research, it is waviness. Scientists use this almost casual-sounding term to describe something quite specific: the amplitude of the north-south loops that the jet stream traces as it circles the planet. A jet stream with low waviness runs in a relatively flat, direct path around the globe, west to east, with only gentle undulations. A jet stream with high waviness bulges dramatically, sometimes swinging thousands of kilometers north into the Arctic before plunging just as far south toward the subtropics, all within a single loop. The question of whether waviness itself has increased over recent decades has become one of the most actively contested threads in the entire field. Some studies, tracking the north-south meandering of the jet stream through direct measures of its latitude and curvature, report a detectable increase in amplitude, particularly in autumn and early winter, and particularly over the sector spanning eastern North America and the North Atlantic. Other studies, examining different metrics or different time periods, find the signal weaker or inconsistent from one season to the next, or masked by the sheer scale of natural year-to-year variability that has always characterized the jet stream: waviness or no waviness. This disagreement is not a sign of sloppy science. It is a sign of a genuinely difficult measurement problem, one where the answer depends heavily on exactly how a slippery, ever-shifting current is defined and quantified in the first place. A related and perhaps more consistently documented change concerns persistence, the tendency of a particular jet stream configuration, wavy or otherwise, to remain locked in place for an unusually long stretch of time, rather than shifting from day to day as weather systems move through. A study published in Communications, Earth and Environment in early 2026 examined 75 years of data on the North Atlantic jet stream during winter and found that subsequent seasonal variability in the jet's position and tilt
had declined by roughly 18 and 14% respectively. In plain terms, this means the winter jet stream over the North Atlantic has become somewhat less variable from week to week than it used to be, tending to settle into a given configuration and hold it longer before moving on. The same research linked this reduced variability directly to changes in regional storm tracks, atmospheric blocking frequency, and the resulting patterns of precipitation and temperature extremes across Europe. A jet stream that moves around less, counterintuitively, can produce more persistent extremes on the ground. Whether that means an unusually long dry spell under a stationary ridge or an unusually prolonged wet period beneath a lingering trough. This brings the discussion to blocking, a term meteorologists use to describe a large, slow-moving area of high pressure that essentially parks itself in the atmosphere and disrupts the normal west-to-east progression of weather systems, sometimes for a week, sometimes for the better part of a month. Blocking patterns are not new. They have always been part of the atmosphere's repertoire, and some of the most extreme weather events of the 20th century, long before anyone was discussing climate change, were tied to exceptionally stubborn blocks. What has changed, according to a growing body of research, is not necessarily whether blocking occurs, but how it interacts with a warming world, and how often certain kinds of blocking configurations recur in specific seasons and specific regions. One especially well-documented example unfolded in the spring of 2026, when meteorologists across the United States described the jet stream settling into what is known as an omega block, named for the shape it traces on a weather map, resembling the Greek letter omega. Rather than allowing systems to move through in the usual rhythm, this configuration held cold air in place over parts of the country for an extended stretch, even as an unrelated ridge of high pressure allowed an early season heat wave to build over the southwest at nearly the same time, and a separate atmospheric river dumped extraordinary rainfall over Hawaii. Meteorologists interviewed at the time were careful in their language, describing the event as consistent with a broader pattern that a changing climate might be expected to produce, without claiming that this single episode could be attributed to climate change on its own. That distinction between an individual event and a long-term trend is one that responsible scientific communication insists on preserving, even when the two are clearly related in a general sense. Seasonal behavior adds yet another layer of complexity. The jet stream does not behave identically in every month of the year. It shifts north in summer as the temperature contrast between the pole and the equator weakens, and it shifts south and strengthens in winter as that contrast sharpens. Researchers examining how this seasonal cycle itself may be evolving have found evidence that certain seasons are more affected by long-term change than others. Autumn and early winter, for instance, appear in several studies to show the clearest signals of increased jet stream waviness and disruption, possibly because this is also the period when Arctic sea ice extent has declined most dramatically in recent decades, altering the temperature contrast that gives the jet stream its shape in the first place. The polar vortex, a separate but closely related feature of the upper atmosphere, has also drawn intense scientific interest in this context. Distinct from the jet stream itself, though closely coupled to it, the polar vortex is a vast, rotating pool of extremely cold air that forms over the Arctic each winter, high in the stratosphere. When the polar vortex is strong and well organized, it tends to keep the jet stream running in a relatively tight, stable pattern, and cold air stays largely bottled up near the pole. When the polar vortex weakens, stretches, or in more dramatic cases, splits into two separate lobes, an event known as a sudden stratospheric warming. The effects can propagate downward into the jet stream over the following 1 to 3 weeks, often producing exactly the kind of amplified, wavy configuration that allows Arctic air to spill unusually far south into the mid-latitudes. Scientists tracking the stratosphere observed several such disruptions during the winter of 2025 into 2026, including a documented split of the vortex into two distinct lobes in early March 2026, an event that forecasters flagged as likely to influence surface weather patterns across North America and Europe in the weeks that followed. None of these individual threads, taken alone, proves a single unified story of jet stream transformation. What they do collectively establish, and what a growing consensus of published research supports, is that multiple independent lines of evidence, examined using different methods, different data sets, and different research groups working largely independently of one another, are converging on a similar general picture. Something about the character of the jet stream, whether measured through waviness, persistence, blocking frequency, or its coupling with the polar vortex above it, does appear to be shifting in ways that go beyond ordinary year-to-year fluctuation. The precise magnitude of that shift, its consistency across different regions of the globe, and its ultimate cause remain the subject of vigorous, ongoing scientific debate. Exactly the kind of debate that characterizes a field still actively working out the details of a real and important phenomenon. If the jet stream is indeed changing, the next question researchers must confront is why. Here, the science becomes both more theoretically rich and more contested, because the honest answer is that several competing mechanisms are almost certainly operating simultaneously, tugging the jet stream in different directions, and untangling their relative contributions is one of the genuinely hard open problems in modern atmospheric science. The most widely discussed candidate mechanism is Arctic amplification, the well-documented phenomenon in which the Arctic region has warmed roughly 4 times faster than the global average over recent decades, according to observational analyses published in the early 2020s and reaffirmed by subsequent studies. This accelerated warming is driven substantially by the retreat of Arctic sea ice, which historically reflected a large share of incoming sunlight back to space. As that reflective ice cover shrinks, the darker ocean surface beneath absorbs far more solar energy, a feedback loop that reinforces itself year after year. The logic connecting this to the jet stream is, at first glance, elegantly simple. Since the jet stream is powered by the temperature contrast between the cold pole and the warm tropics, and since the Arctic is warming faster than the tropics, that contrast should be shrinking. A weaker temperature contrast, the reasoning goes, should produce a weaker, wavier, more easily disrupted jet stream, prone to the kind of extended blocking patterns described earlier. This hypothesis, often associated with early research by scientists including Jennifer Francis and Stephen Vavris, proved enormously influential and helped popularize the idea of a link between Arctic warming and extreme mid-latitude weather, sometimes summarized under the phrase warm Arctic, cold continents. And subsequent research has continued to find support for aspects of this connection. Multiple studies reviewed in a comprehensive analysis published in late 2024 concluded that Arctic amplification does appear to favor the occurrence of mid-latitude cold extremes during winter, with the warm Arctic pattern corresponding fairly reliably to blocking anticyclones and resulting cold outbreaks over Eurasia and North America. However, and this is a point that responsible science communication must emphasize clearly, not every study agrees, and the disagreement is not a fringe position. It comes from serious, well-regarded research groups working with the same underlying physics. Other analyses, including work published by researchers such as Russell Blackport and colleagues, have found that when climate models are run under controlled conditions, isolating the effect of sea ice loss specifically, the resulting weakening of the jet stream and increase in blocking frequency is often much smaller than the observational correlation would suggest, or in some model configurations, barely present at all. Some studies examining the eddy feedback processes that maintain jet stream strength have even found a reduced risk of certain kinds of cold extremes as Arctic sea ice continues to decline, the opposite of what the simplest version of the Arctic amplification hypothesis would predict. How can two lines of research, both grounded in solid physics, arrive at such different conclusions? Part of the answer lies in the sheer complexity of the atmosphere-ocean system, where dozens of interacting processes operate on overlapping timescales, making it extraordinarily difficult to isolate the specific contribution of any single factor, such as sea ice loss, from the noisy background of natural variability, tropical influences, and other forms of climate change occurring simultaneously. Reviews of this literature, including one published in the Nature Review's Earth and Environment Journal in late 2025, have concluded that a full mechanistic account likely involves not a single dominant driver, but a shifting balance among several. Arctic amplification, warming ocean surface temperatures at lower latitudes, changes in tropical convection patterns, stratosphere-troposphere coupling, and the direct thermodynamic effects of a warmer, moister atmosphere on wave propagation. That last factor deserves its own explanation, because it represents an alternative, competing mechanism to the Arctic amplification story, one that some researchers argue may ultimately prove more important, at least for the fastest-moving cores of the jet stream. This mechanism does not rely on the Arctic warming faster than the tropics at all. Instead, it points to a different consequence of a warmer atmosphere. Air above the tropics can hold substantially more moisture than air above the poles, because warm air holds more water vapor than cold air under basic thermodynamic principles. As the planet warms, this moisture difference between tropical and polar air masses is expected to grow, and because water vapor releases latent heat when it condenses, this asymmetry can actually intensify rather than reduce certain measures of the temperature contrast that powers the jet stream, at least at the altitudes where the fastest winds are found. Research using this framework, including modeling work centered at the University of Chicago and the National Center for Atmospheric Research, projects that the very fastest jet stream winds could continue to accelerate as the planet warms, even while broader measures of the jet stream elsewhere show weakening or increased waviness. It is a reminder that the jet stream is not one simple thing behaving one simple way. It is a family of related phenomena at different altitudes and latitudes, each responding to the changing climate through somewhat different physical pathways, sometimes pulling in opposite directions from one another. Rossby waves themselves, the large-scale meanders that give the jet stream its wavy character in the first place, add another dimension to this puzzle. These waves are not random. They are governed by well-understood fluid dynamics, and their behavior depends heavily on the underlying temperature structure of the atmosphere. Some researchers have proposed that specific configurations of these waves, sometimes described as quasi-resonant amplification, can become temporarily locked in place under certain atmospheric conditions, amplifying and holding position for unusually long stretches. which would help explain the extended blocking events and heat waves that have drawn public attention in recent years. This hypothesis, associated in part with research by Kai Kornhuber and other atmospheric dynamicists, remains an active area of investigation, with ongoing debate about how frequently these resonant conditions actually occur and how confidently they can be identified in observational data, as opposed to idealized model simulations. The honest summary that most researchers in this field would offer, if pressed, goes something like this. The jet stream is very likely responding to human-driven climate change in more than one way at once, through more than one physical mechanism. And those mechanisms do not always point in the same direction. Some processes tend to weaken and destabilize the jet stream, favoring wavier, more persistent, more blocking-prone behavior. Others tend to strengthen its fastest cores. Still others may shift its average position poleward without dramatically altering its shape at all. Untangling exactly how much each of these processes contributes, in which season, in which region of the planet, remains one of the central open questions driving the current wave of research. And it is precisely the kind of layered, sometimes contradictory scientific picture that a documentary owes its audience the honesty to portray, rather than flattening it into a single, simple narrative of cause and effect. Whatever the precise mechanisms turn out to be, the practical consequences of a shifting jet stream are not confined to scientific journals. They arrive on the ground, in the form of weather that people actually live through. And it is here that the abstract physics of upper atmosphere wind patterns becomes something far more tangible. Heat waves offer perhaps the clearest example of how jet stream behavior translates into lived experience. When the current develops a persistent northward bulge, a ridge of high pressure can settle beneath it and remain locked in place for days or weeks at a time. Under such a ridge, skies stay clear, winds stay weak, and the ground itself begins to bake under relentless, unbroken sunshine, since there is no passing weather system to interrupt the buildup of heat. Researchers studying major breadbasket regions, the agricultural heartlands that produce a large share of the world's grain, have found that amplified Rossby wave patterns can occasionally align in a way that produces simultaneous heat waves across multiple major growing regions at once, a phenomenon with obvious implications for global food supply that goes well beyond the discomfort of any single heat wave in any single country. Floods represent something close to the mirror image of this same dynamic. Where a heat wave results from a stubborn ridge holding dry air in place, catastrophic flooding often results from an equally stubborn trough, or from a jet stream configuration that repeatedly funnels moisture-laden storm systems along the same track, one after another, into the same unfortunate stretch of geography. When the jet stream stalls in this way, a region that might ordinarily absorb a single heavy rainfall event without much difficulty can instead receive the equivalent of several such events back to back, overwhelming rivers, soil, and drainage systems that had no time to recover between storms. The extraordinary rainfall recorded over Hawaii during the same March 2026 weather episode that brought an omega block and Arctic outbreak to the mainland United States illustrated this vividly. More than 60 centimeters of rain fell in a matter of days, a direct consequence of the same large-scale atmospheric configuration that was simultaneously delivering a blizzard to the Great Lakes and a heat wave to the southwest. Three dramatically different kinds of extreme weather, all traceable to variations along a single disrupted jet stream. Wildfires, too, carry a jet stream signature. though an indirect one. The same persistent high-pressure ridges that produce heat waves also tend to dry out vegetation over extended periods, priming landscapes to burn. When that dryness combines with the gusty, often erratic surface winds that can accompany a wavy, disrupted jet stream pattern, the ingredients for rapid fire spread come together in a way that has become tragically familiar to residents of fire-prone regions across the western United States, southern Europe, and parts of Australia in recent fire seasons. Cold outbreaks, somewhat paradoxically, belong on this same list of jet stream consequences, precisely because a warming planet does not mean the disappearance of extreme cold. It can mean, at least in some regions and some winters, cold arriving in more concentrated, more disruptive bursts. When the polar vortex weakens or splits, and the jet stream responds with an amplified southward dip, Arctic air that would normally stay bottled up near the pole can spill deep into the mid-latitudes, sometimes producing record low temperatures in places entirely unprepared for them. The severe cold events that struck the central United States and Scandinavia in January 2024, and the further disruptions tracked by stratospheric researchers through the winter of 2025 into 2026, fit this pattern. An amplified jet stream configuration, paired with a stretched or split stratospheric polar vortex, delivering cold air far beyond its usual territory. Utility grids, transportation networks, and water systems designed around historical temperature ranges can be caught badly off guard by these events, a vulnerability starkly illustrated by the widespread grid failures that accompanied a major cold outbreak in Texas in February 2021, an event that prompted significant infrastructure investment specifically intended to reduce the risk of similar failures in future cold snaps. Agriculture sits at the intersection of nearly all these effects, since crops are exquisitely sensitive to the timing, not just the intensity, of weather extremes. A late spring frost, arriving after fruit trees have already begun to flower, can devastate an entire season's harvest in a matter of hours. And researchers have linked the timing of unusual late-season cold snaps in temperate agricultural regions to jet stream configurations that allow cold air to intrude well after the calendar would normally suggest such intrusions should have ended. Drought, driven by a persistent ridge, can stunt crop development over an entire growing season, while flooding, driven by a stalled trough, can drown fields at the opposite extreme. Farmers, insurers, and agricultural economists increasingly track jet stream forecasts not as an abstract scientific curiosity, but as a genuinely practical input into decisions about planting dates, irrigation, and crop insurance. Transportation feels these effects too, in ways both mundane and occasionally dramatic. Commercial aviation has long exploited the jet stream's tailwind on eastbound transatlantic and transpacific routes, shaving substantial time and fuel off flights that ride the current, while westbound flights route around it to avoid the opposing headwind. But as some research suggests, the fastest cores of the jet stream may be intensifying. Aviation researchers have also raised the possibility of increased clear air turbulence, a form of rough air that occurs without visible clouds to warn pilots in advance, and which has already been implicated in a number of serious in-flight injury incidents in recent years. Ground transportation faces its own jet stream-linked disruptions, from blizzards that shut down highway networks to sudden ice storms that can strand travelers for days when a wavy jet stream configuration delivers precisely the wrong combination of cold air and moisture at once. Energy systems, meanwhile, must contend with both ends of the temperature spectrum that a disrupted jet stream can produce. Extended heat waves drive electricity demand toward its seasonal peak, just as some power generation, particularly certain types of thermal and nuclear plants that rely on river or ocean water for cooling, can become less efficient in unusually warm conditions. Extended cold outbreaks push demand toward the opposite peak, often straining natural gas supply chains and electrical grids simultaneously. Exactly the failure mode that unfolded during the Texas cold event, when frozen equipment and surging demand combined to catastrophic effect. Human health, finally, bears perhaps the most direct cost of all. Prolonged heat waves are already recognized by public health researchers as among the deadliest weather phenomena on the planet, particularly for elderly populations, outdoor workers, and communities lacking reliable access to air conditioning. Precisely the populations least equipped to cope with a heat event that a stalled jet stream configuration has allowed to persist for an unusually long stretch. Cold outbreaks carry their own serious health toll, from hypothermia and carbon monoxide poisoning linked to emergency heating measures to the strain that sudden temperature swings place on cardiovascular systems, particularly among older adults. None of this establishes that any single heat wave, flood, or cold snap was caused by climate change acting through the jet stream in a simple, direct line. Individual weather events remain the product of many overlapping factors, and scientists are careful to preserve that distinction. What the growing body of research does suggest is a shift in the underlying odds, a subtle but consequential change in how often certain jet stream configurations occur, and therefore in how often the extreme weather they produce is likely to visit any given region in the years ahead. For all that has been learned about the jet stream over the past 80 years, the honest state of the science today is that the list of open questions remains at least as long as the list of settled answers, and serious researchers are quick to say so. This is not a weakness of the field. It is a sign of a discipline still actively working through a genuinely difficult problem, one where the atmosphere itself seems to resist easy summary. Perhaps the largest unresolved question concerns disentangling long-term climate-driven trends from the atmosphere's own enormous natural variability. The jet stream has never behaved with perfect consistency, even in eras with no meaningful human influence on climate at all. It responds to the state of the tropical Pacific during El Niño and La Niña events, to the phase of longer cycles like the North Atlantic Oscillation and the Pacific Decadal Oscillation, and to volcanic eruptions that inject reflective particles into the stratosphere and temporarily alter atmospheric temperature structure. Separating a genuine climate-driven shift in jet stream behavior from this constant background noise requires extremely long observational records, which is precisely why researchers place such value on satellite archives and reanalysis datasets that now stretch back 70 years or more. Even so, some of the changes described earlier in this film, particularly around waviness and blocking frequency, remain within a range where different research teams, using slightly different methods or slightly different time periods, can arrive at meaningfully different conclusions. Resolving this will likely require not a single decisive study, but the patient accumulation of additional decades of data, combined with continued refinement of the statistical techniques used to isolate long-term signals. A second major open question concerns regional variation. Much of the research discussed so far has focused on the North Atlantic and North American sectors, in part because these regions have the longest and most complete historical weather records, and in part because they affect some of the world's most closely studied and heavily populated regions. But the jet stream circles the entire globe, and its behavior over the North Pacific, over Eurasia, over the Southern Hemisphere, and over less densely instrumented regions may be following quite different trajectories.
The 2026 study projecting a strengthening, southward shifting westerly jet over Central Asia illustrates this regional specificity vividly. Rather than a single global story of weakening and increased waviness, this particular current is projected to intensify, with effects on regional moisture supply that could actually reduce drought risk in parts of Central Asia, even as other regions potentially see increased blocking and disrupted weather patterns. Scientists studying the Southern Hemisphere jet stream, meanwhile, have found their own distinct pattern of change, driven substantially by the recovery of the ozone layer over Antarctica, interacting with rising greenhouse gas concentrations, a mechanism with no direct equivalent in the Northern Hemisphere story. Building a genuinely global picture of jet stream change, one that does justice to these very different regional trajectories, rather than flattening them into a single simplified narrative, remains an enormous undertaking, and one that international research collaborations are only partway through completing. A third open question, perhaps the most consequential for everyday forecasting, concerns predictability itself. Even if scientists eventually achieve a complete theoretical understanding of how a warming climate reshapes the jet stream over decades, that understanding would not automatically translate into the ability to predict, weeks or months in advance, exactly when and where a specific blocking event or cold outbreak will occur. Weather forecasting and climate projection operate on fundamentally different timescales and answer fundamentally different questions. And one of the active frontiers in this field involves so-called sub-seasonal to seasonal forecasting, an effort to extend reliable prediction beyond the traditional 10-day forecast window and out towards several weeks or a couple of months, precisely the timescale on which a persistent blocking pattern might be identified before it fully develops. Progress here has been real but incremental, and meteorologists generally caution that confident forecasts of specific extreme events more than roughly 2 weeks in advance remain beyond current capability, even as the broader statistical odds of certain patterns occurring in a given season continue to improve. The observational infrastructure underpinning all of this research also continues to expand. Space agencies have multiple next-generation missions either recently launched or in active development, specifically intended to improve wind and temperature measurements at the altitudes where the jet stream operates. Programs coordinated by NOAA and the European Meteorological Satellite Organization, EUMETSAT, are working to extend and improve the existing network of polar orbiting and geostationary satellites, incorporating more advanced infrared sounders and microwave instruments capable of resolving finer vertical detail in atmospheric temperature profiles than earlier generations of instruments could achieve. Ground-based radar and profiling networks are being modernized in parallel, and international efforts to expand the balloon-based radiosonde network into historically underrepresented regions, including parts of Africa, South America, and the open ocean, aim to close persistent gaps in global coverage that currently limit how confidently scientists can characterize jet stream behavior in less studied parts of the world. Computational modeling, too, is advancing on multiple fronts simultaneously. Traditional physics-based climate models continue to improve in resolution, allowing them to represent smaller-scale atmospheric features
including narrow jet cores and sharp frontal boundaries, with greater fidelity than earlier generations of coarser models ever could. At the same time, a newer generation of machine learning-based weather and climate models, trained on the enormous archives of historical reanalysis data described earlier, has begun to demonstrate genuinely competitive and, in some specific applications, superior forecasting skill compared with traditional physics-based approaches, while requiring a small fraction of the computing power. Several major research groups and national weather agencies are actively exploring how these machine learning approaches might be combined with, rather than simply replacing, traditional physical models, potentially offering new tools for exploring exactly the kind of subtle, long-term jet stream trends that have proven so statistically challenging to pin down using conventional methods alone. International scientific coordination continues to play a central role in advancing this research. The World Meteorological Organization maintains ongoing working groups specifically focused on polar and mid-latitude atmospheric dynamics, bringing together researchers from dozens of countries to standardize observational methods and share data across national boundaries. Since no single country's weather agency, however well-resourced, could hope to characterize a phenomenon that circles the entire planet using only its own domestic observation network. The Polar Amplification Model Intercomparison Project, a coordinated international modeling effort launched specifically to investigate the causes and consequences of Arctic and Antarctic amplification, has brought together dozens of climate models from research centers around the world to systematically test competing hypotheses about how polar warming influences the jet stream, providing exactly the kind of controlled, comparable experimental framework that individual research groups working alone could never assemble on their own. What emerges from all of this ongoing effort is not a field waiting passively for a single breakthrough that will resolve every remaining question at once. It is, instead, a steadily advancing frontier, where each new satellite mission, each expanded model ensemble, each additional decade of observational data narrows the uncertainty a little further, even as new questions inevitably arise alongside the answers. Researchers studying the jet stream today are, in a very real sense, assembling a puzzle whose full picture may not become clear for another generation. Built one careful measurement, one peer-reviewed study, one incremental model improvement at a time. To understand how these scientific debates translate into lived, documented weather, it helps to walk through a handful of specific episodes that researchers have studied closely in recent seasons. Not because any single event proves a broader theory, but because each one illustrates, in concrete terms, how the abstract physics discussed so far actually plays out across a real landscape, in real time, affecting real people. Consider the sequence of events that unfolded across North America in the winter stretching from late 2025 into early 2026. In early December 2025, forecasters tracking the stratospheric polar vortex observed it splitting into two distinct lobes, a disruption that temporarily weakened its usual tight, well-organized structure. Through the following weeks, the vortex began to reorganize and strengthen, a recovery that extended range forecasts linked to an increased likelihood of Arctic air intrusions into the central and eastern United States by mid-January. Meanwhile, across the Atlantic, forecasters described a more variable pattern developing over Europe, with alternating episodes of ridging and blocking near Greenland and the North Atlantic, the kind of configuration that can redirect Arctic air toward northern and western Europe, even when the broader vortex trends toward a more stable zonal flow. By early March 2026, a further disruption emerged. Atmospheric scientists tracking planetary wave activity documented strong upward propagation of energy from the mid-latitude troposphere into the Arctic stratosphere, a textbook signature of what meteorologists call a sudden stratospheric warming event, which again split the polar vortex into two lobes. Researchers monitoring this event noted, with appropriate scientific caution, that such disruptions typically influence surface weather over the following 1 to 3 weeks, while also acknowledging that the exact evolution remained uncertain, since late winter stratospheric warmings can sometimes simply transition into the ordinary seasonal breakdown of the vortex that occurs every year as spring approaches, rather than producing any unusual surface impact at all. Roughly 10 days later, the surface consequences became visible. An omega-shaped blocking pattern settled over North America, holding cold air over the Great Lakes region long enough to produce a major blizzard, while a separate ridge allowed an early-season heat wave to build across the southwest, and a moisture-laden flow funneled extraordinary rainfall into Hawaii. 3 dramatically different extremes, unfolding simultaneously, each traceable to a different lobe of the same disrupted, wavy jet stream configuration. This kind of layered, multi-week case study, moving from stratospheric observation through tropospheric response to surface impact, illustrates why atmospheric scientists increasingly emphasize the vertical coupling between the stratosphere and the jet stream below it, rather than treating the two as entirely separate systems. It also illustrates something important about scientific communication. Meteorologists studying this sequence in real time consistently used careful, conditional language, describing conditions as consistent with expected patterns under a changing climate, without ever claiming that this specific sequence of events was directly caused by climate change, in some simple, deterministic sense. That distinction between describing a statistical tendency and asserting a direct causal chain for any single event sits at the heart of how responsible climate science communicates uncertainty. And it is a distinction worth preserving carefully in any documentary account of this subject. A second instructive case study comes from the Southern Hemisphere, where an international team of meteorologists publishing their findings in the Proceedings of the National Academy of Sciences applied a specialized statistical technique known as the storylines methodology to disentangle how much of the observed change in the Southern Hemisphere jet stream could be attributed directly to global warming as opposed to natural variability or other factors. This approach, developed specifically because traditional climate modeling struggles with the deep uncertainty inherent in projecting a single, particular future rather than a broad statistical range, allowed the researchers to explore multiple physically plausible scenarios simultaneously, each internally consistent with the known laws of atmospheric physics. Their conclusion? That roughly half of the recently observed jet stream shift in the Southern Hemisphere traces back to human-driven warming, represents exactly the kind of carefully quantified, appropriately hedged finding that characterizes rigorous science in this field. Not a claim that climate change explains everything, and not a dismissal of climate change's role either, but a specific, falsifiable estimate that future research can test, refine, and potentially revise as additional data accumulates. A third thread worth following concerns the relationship between the jet stream and the broader ocean circulation systems that some of the same viewers drawn to this documentary may already have encountered in other contexts, including the slow overturning circulation that carries warm surface water northward through the Atlantic and returns cold, dense water southward at depth. While that overturning circulation operates on a fundamentally different timescale and through different physical mechanisms than the jet stream, the two systems are not entirely independent.
Both respond to changes in the temperature contrast between polar and tropical regions. Both are influenced by the freshwater input that accompanies melting ice. And some researchers have begun exploring whether long-term changes in one system might, over sufficiently long timescales, influence the other through shared boundary conditions in ocean and atmospheric temperature. This remains a genuinely exploratory area of research, with far less scientific consensus than the more direct jet stream studies described earlier in this film. And it is mentioned here not as an established finding, but as an honest illustration of how interconnected Earth's major circulation systems ultimately are, and how much interdisciplinary work remains before scientists can offer a fully integrated picture of how a changing climate reshapes the planet's major circulation patterns together, rather than one system at a time. A fourth and final case study returns to a more everyday, and in some ways more immediately consequential, application of jet stream research: aviation safety and efficiency. As commercial airlines increasingly rely on real-time jet stream data to optimize flight paths, shaving fuel costs and flight times by riding favorable tailwinds on eastbound routes, the same data streams that support this optimization also feed directly into the scientific record described throughout this film. Aircraft-based turbulence reports, collected automatically from thousands of flights daily and shared through international meteorological data exchange programs, have allowed researchers to track a modest but measurable increase in the frequency of clear air turbulence encounters over the North Atlantic corridor in recent decades, a trend that several published studies have linked to the same increasing temperature contrast between the tropical upper troposphere and the surrounding atmosphere that separate modeling work suggests is intensifying the fastest cores of the jet stream. Airlines and aviation regulators have responded with updated turbulence forecasting tools and revised guidance on seatbelt use during cruise, a comparatively small but tangible example of how evolving jet stream science translates directly into changed practice, well outside the world of academic publishing. Taken together, these case studies, spanning a single disrupted North American winter, a Southern Hemisphere statistical reconstruction, an emerging and still uncertain question about ocean-atmosphere coupling, and the everyday world of commercial aviation, demonstrate something that abstract discussion of mechanisms alone cannot fully convey. This is not a purely theoretical scientific debate confined to journals and conferences. It is a live, evolving picture, continuously updated by new data, new events, and new analysis, in which each individual season adds another data point to a puzzle that researchers around the world are actively assembling in real time, piece by careful piece. It is worth noting, too, that this expanding observational effort no longer belongs exclusively to national weather agencies and university research departments. Citizen science networks, coordinating thousands of volunteer weather station operators who share real-time surface pressure, temperature, and wind data, have begun contributing meaningfully to the fine-grained surface observations that help validate how well satellite and model-based estimates of jet stream position actually correspond to conditions experienced at ground level. Ocean-based sensor networks, including autonomous drifting buoys that measure sea surface temperature across remote stretches of open water where research vessels rarely travel, feed directly into the same reanalysis data sets that allow scientists to reconstruct decades of jet stream behavior, since the ocean's surface temperature is itself one of the fundamental ingredients shaping the atmospheric temperature contrasts that give the jet stream its structure in the first place. None of these individual contributions, a backyard weather station, a drifting ocean buoy, a single research flight, resolves the larger scientific questions on its own. But collectively, this growing,
increasingly democratized web of observation, spanning government agencies, university laboratories, commercial airlines, and ordinary volunteers checking a home weather station each morning, represents the quiet infrastructure, making it possible to study a phenomenon this vast, this invisible, and this consequential, with a degree of confidence that earlier generations of meteorologists, working from balloon launches and scattered ship reports alone, could only have imagined. There is a temptation, when telling a story like this one, to reach for a tidy conclusion, a single sentence that resolves the mystery and tells the audience exactly what to feel. The honest version of this story resists that temptation, because the science itself resists it. The jet stream is not collapsing. It is not vanishing. It has not broken in some catastrophic, irreversible way that threatens to end weather as we know it. Nothing in the peer-reviewed literature supports language that dramatic, and any documentary that reached for it would be trading scientific accuracy for cheap and unearned alarm. What the evidence does support is something quieter, and in its own way more interesting. A river of wind that has circled this planet for as long as there has been an atmosphere to hold it, responding, as it always has, to the temperature contrasts that give it life, is now responding to a temperature contrast that human activity has begun to reshape. The Arctic is warming faster than the tropics. The oceans are absorbing heat and moisture in patterns different from those of a century ago. The stratosphere and troposphere are exchanging energy in ways researchers are still working to fully characterize. Each of these shifts leaves its own fingerprint on the jet stream, and those fingerprints do not always point in the same direction. Which is exactly why the scientific picture remains genuinely open rather than settled into a single, simple narrative. Consider for a moment what this current actually represents. It is not a machine with a single lever that either works or breaks. It is closer to a dynamic equilibrium, a balance perpetually being struck and restruck between competing forces. The cold of the pole against the warmth of the tropics, the spin of the planet against the flow of the air, the moisture of a warming atmosphere against the dry chill of the upper stratosphere. For millions of years before any human stood beneath it, this balance shifted with ice ages and warm periods, with volcanic eruptions and changes in solar output, always finding some new configuration, always continuing to steer weather across the hemispheres it circles. What is different now is not that the jet stream is changing, since change is, in some sense, what it has always done. What is different is the speed and the specific direction of the forces now acting on it. Forces traceable in large part to a relatively narrow band of decades, during which humanity's collective activity began altering the composition of the atmosphere itself. Scientists studying this system today occupy an unusual and rather admirable position. They are documenting a natural phenomenon in real time, watching for signals within decades of data, while openly acknowledging how much remains genuinely uncertain, resisting the pull toward premature certainty in either direction, refusing to claim more than the evidence supports, whether that evidence points toward alarm or toward reassurance. This is what careful science looks like from the inside. Less a series of dramatic announcements, and more an accumulation of careful measurements, competing hypotheses tested against one another, and a steady, patient narrowing of what remains unknown. For those of us living beneath this invisible current, largely unaware of its daily position, its speed, its wave pattern on any given day, the practical takeaway is neither panic nor indifference, but something closer to attentiveness. The weather forecasts checked each morning. The unusually persistent heat wave that seems to refuse to break. The cold snap that arrives later or harder than expected. The flood that lingers longer than the historical record would suggest it should. All of these carry, somewhere in their origin, a signature written high above the clouds, in a river of wind that has been shaping life on this planet since long before anyone thought to look for it, and that scientists around the world are now watching with a degree of care and precision unmatched in the history of atmospheric science. Whether the coming decades will bring a jet stream that settles into a new, stable configuration, or one that continues evolving in ways not yet fully anticipated by even the most sophisticated models available today, is a question that remains, quite genuinely, open. It is a question that satellites currently in orbit will help answer, that weather balloons launched twice daily from stations scattered across the globe will continue to inform, that the next generation of climate models, sharper and more detailed than anything available today, will refine further still. The jet stream has always shaped life on Earth, quietly, invisibly, from an altitude few people ever think to consider. Whether its recent behavior marks a temporary fluctuation within the range of natural variability, or the early signature of a longer transformation still unfolding, is a question that science continues to explore. One careful measurement at a time, high above the world it continues, in ways both subtle and profound, to shape.